In this video, we're going to look at the heat energy questions from the mechanisms and structures course notes on energy, work, power, and efficiency. So we'll start off by writing up what our formula for heat energy is. It's that heat energy is equal to the mass in question multiplied by the specific heat capacity of that mass multiplied by the change in temperature, where energy is in joules, mass is in kilograms. Specific heat capacity is this slightly more complicated unit. It's joules per kilogram per degree heated, and that could be degrees Celsius or degrees Kelvin. It means the same thing in this case because our delta T is going to be the difference in temperature, and the difference in temperature in Celsius or Kelvin is the same because when we subtract one from the other, the gap is the same either way. So whether we're working in Celsius or Kelvin for this, it's not going to change our value for C or our value for delta T. So we can use them in this context interchangeably. Question 1 says, calculate the heat energy required to heat 2 kilograms of water from a temperature of 20 degrees until it begins to boil. So let's see what we have here. We're told the mass is 2 kilograms, and that is the right units to be using. Our value for C is not given in the question. Usually this would be given to us in assessment style questions. Don't worry about not having it here. But it's given in the course notes as 4,180 joules per kilogram per degree Kelvin. And it doesn't matter. Sometimes it'll say per degree Celsius. It'll be the same number of 4,180. And our delta T is the change in temperature. So we're going from 20 degrees up to boiling. So that's 100 minus 20, which is equal to 80 degrees. And it's 80 degrees Celsius, but this would be the same. It would be 80 degrees Kelvin, the difference between the two. So try not to worry too much about the fact that one says Kelvin there and one says Celsius. A difference in temperature, we could just write the difference as 80 Kelvin, and that would be the same too. So don't be concerned about that. But we now have all the information we need, so we can write that EH is equal to MC times delta T. M is 2, C is 4,180, and delta T is 80. And so we can multiply these three together to get the value for the energy required to raise water by this much temperature difference. And the answer we get here is 668,800. And of course, that's in joules. So that's question 1. Question 2 is a bit trickier. If the hull has dimensions of 8 times 30 times 10, assuming no heat loss, calculate the amount of heat required to raise the temperature of the air in the hull from 10 to 20 degrees. The density of the air is 1.3 kilograms per meter cubed, and specific heat capacity is 850 joules per kilogram per degree Kelvin. So there's some things we recognise in there that we'll see within our formula, and some things that we don't. So let's start writing down a couple of things that we do know. We know there's a change in temperature from 10 to 20. So 20 minus 10 is 10 degrees Celsius. And we're told the specific heat capacity that's value for C is 850 joules per kilogram per degree Kelvin. So we have these two. The only thing we don't have is the mass. Now, this is something that goes slightly beyond the scope of the unit, but it's very well established within engineering and physics at this level, which is how do we find the mass if we know the volume of a space and the density of the thing inside the space. So let me write this down. We know the volume of the hull because the volume of a cuboid, which any room is, if it's got a rectangular floor and a height, is going to be length times breadth times height. Now we're not told which one is which here, but we can assume that 30 meters certainly isn't the height. So let's just assume that it's 8 times 30 times 10 in that order. It doesn't really matter for the volume, so it's 8 times 30 times 10. So this is the volume of the hull, the volume of any cuboid, if we know the three sides. And that's 2,400 meters cubed. Now this maybe gets us thinking that if the air is 1.3 kilograms per meter cubed, if we multiply this volume by the density then maybe we'll get the mass of air, and that will give us the M we need for our formula. Indeed, that is correct. The formula for mass is equal to rho. This is a Greek letter which represents density, and in V, volume, which is the volume of whatever space it's in. So we're saying air has this density and it's in this space. So the 1.3, I'm taking that from the question, 1.3 kilograms per meter cubed. I should write down here. And that's multiplied by the volume, which is 2,400. So probably not the type of question we give in the assessment, it's slightly beyond what we do in the unit, but it's something that's going to be useful to know, and we can find out that the mass of air is 3,120 kilograms. In that space. So we now have a value for M that we can use, which helps us greatly, because we now have the three things we need to work out the energy. We have M, C, and delta T. So we can now write the heat energy required to heat this hull by 10 degrees is going to be MC delta T. It's going to be equal to 3,120 times 850, which are given in the question, multiplied by 10, which we're told the increase in temperature is. And the answer we get from this is 26,520,000 joules. Or 26.52 megajoules if you prefer. But yes, there was a bit of extra work there, but even without that, we should have been able to identify this information we required from the question, and with a little bit of additional information, we can use this to work out the mass. So let's now look at question 3. In question 3, we're told the heating element in a shower can produce heat energy at a rate of 7 kilojoules per second. Water enters the system at 15 degrees, it's heated to 40 degrees, and we're asked to find the flow rate in litres per second and state any assumptions we've made. So let's see what we know already. Because we're dealing with water, we can write down straight away that C will be equal to 4,180 joules per kilogram per degree Kelvin. The difference in temperature we can see is 40 minus 15, which is 25 degrees Celsius. And then we are told that in 1 second, this much energy is used. So we can write down heat energy equal to 7 kilojoules to 7,000 joules. And maybe we'll say in brackets here, in 1 second. We don't need to worry about time in this because we're asked to find out how much water is flowing in 1 second as well. So we can base all of our calculations around having 7,000 joules, because we're saying this whole thing takes place in 1 second. That's what we're interested in finding out. So our formula is heat energy is equal to M times C times delta T. So we can rearrange this to find the mass. Mass is equal to heat energy divided by C and delta T. We divide by everything that's multiplied by M to get M by itself. And we can put in our values. We're going to have 7,000 for E, and then we're going to have 4,180 times 25 on the bottom there for our values for C and delta T. And if we put in these values, we can answer something like this, 0.067, and this will be in kilograms. This is how much water is flowing per second, 0.067 kilograms. Now, something we're not told in the question, but we know from elsewhere, and we would be given this in assessment, that 1 litre of water has mass 1 kilogram. So this means if we have 0.067 kilograms, we have 0.067 litres. And because we know this is the energy required in 1 second, this is 0.67 litres per second. So that's how we work that out. We take the energy used in 1 second, we use that to find the mass, and we know what we know about water, that 1 kilogram is 1 litre, to say this is 0.067 litres per second. Again, there would have to be a few more pieces of information given to you for that to be anything like an assessment question, but it's in the range of what we've talked about in the course. And the final question, question 4, asks us to find a final temperature. So this is something slightly different. We're using the same formula, we actually have all the information we need for us to find the final temperature. So let's have a look at what's going on here. First of all, we're given the heat energy in this question. It's 57 kilojoules, which is 57,000 joules. Always convert into joules. And we're told that the mass is 1.7 kilograms. That's great, that's the right units. And we're told that the specific heat capacity is 2.7 kilojoules per kilogram per degree Kelvin. Now again, watch out for kilojoules. We need to convert this as well. So this is going to be 2,700 joules per kilogram per degree Kelvin. So what we're actually been asked to find out here is delta T. First of all, what is delta T? That's not the same thing as the final temperature. There's a little bit of extra work to do. We have to find out delta T first to find the final temperature. So let's work this out. So our heat energy will be equal to mass times specific heat capacity times change in temperature. And we can rearrange our formula again to get change in temperature. This will be to 57,000 divided by 1.7 times 2,700 in the bottom of the fraction. And make sure you put this in a calculator. Do 57,000 divided by, then open brackets, 1.7 times 2,700. So you're dividing 57,000 by both of them, or use the fraction button in the calculator to make sure we're doing things in the correct order here. Entering this into our calculator, we get an answer of 12.4. And it's a change in temperature. It can be degrees Celsius or degrees Kelvin. I'm just choosing to write degrees Celsius. It's a change in temperature. So that's what we get. Let's ask the question, what is the final temperature? Well, if we started off at 3 degrees and we've changed our temperature by 12.4 degrees, then our final answer is going to be 15.4 degrees Celsius. Because delta T, if you remember, is the final temperature minus the starting temperature. So this is our final temperature, and that's our start. Well, 15.4 minus 3 would give us delta T in the middle. So to find the final temperature, take our starting temperature, add on delta T, and you'll get our final temperature there. And that's how we solve that type of question. So if we're ever asked to find the starting temperature, our final temperature, and we're given the other one, we can add or subtract delta T once we've worked that out using our formula. And that concludes all of the questions on heat energy from the course notes. So we can just see here, move this back up to see everything. These are the types of questions. So some straightforward, some with a few extra tricks in them, but we'd have to, as I said, give more information to give anything like that in an assessment style question.